Hi guys. So this is going to be the first part of an ongoing series on GLSL inside of TouchDesigner, specifically focused on some of the techniques that are gaining a lot of popularity on websites like ShaderToy, and there seems to be a definite interest in the TouchDesigner community towards learning some of those techniques and incorporating them into touch projects. So it's something that is very hard to grasp for beginners, and there's definitely not a lot of good resources out there for people just getting started with some of those techniques. It took me a long time to wrap my head around even the basics of those techniques and understanding that all of that is happening inside of a single fragment shader. There's no geometry, there's no SOPs, there's nothing. It's all happening inside of one shader. That's something that I think for people new to ray marching, but also GLSL, it's a very hard thing to grasp. So hopefully my goal is to kind of make the technique a little bit more accessible and hopefully people in the touch designer community who are a little more experienced with it than I am will contribute and help to grow our knowledge base, because I think it's a really cool technique with a lot of creative potential once you get it up and running and sort of get the basic framework figured out. But it's just getting to that point is really hard. Um, Anyways, with that all said, let's get started. In this first tutorial, we're not gonna be making anything crazy yet. I just kind of want to get everyone on the same page and sort of introduce the topic of distance functions, because that's really the foundation for all of these things that you're seeing on Shader Toys. Like, you have to understand these basic techniques first before any of that is going to make sense. Um, when you first create a GLSL top, some of this text out will be created for you with some sample code inside of it. So usually one of the first things I do is just like delete these comments. This is just like an example of how you would sample a texture inside of your shader, which we're not really going to be using. And then this is an example of declaring a uniform, which is something that we will probably get to towards the end of this tutorial. In older versions of GLSL, there was actually a built-in variable called GL frag color, and that is where you would write your final output color to in your shader. In newer versions, like in Touch, you have to actually declare this variable yourself. Touch will do it for you when you create your GLSL top. So the out specifier basically means that this data will be output to the next stage of the graphics pipeline, which in this case is just writing to the frame buffer, which is what you see here in this op viewer. It's a frame buffer, and it's a vec4, meaning it is a 4-element vector, so it has 4 components. In this case, we have R, G, B, and A as our components, and then this, of course, is just the name of the variable. All of our code will be inside of this main function, at least for now. Eventually, we'll be writing some of our own functions as we get into some of the more advanced techniques, but for now, we'll just use this. They also, Touch will declare a variable for you here called color. Again, it's a vec4. If you aren't familiar with some of the different ways of constructing vectors inside of GLSL, that's definitely something worth reviewing, because that's going to come up a lot in the way that we write GLSL. It has a lot of built-in ways to kind of manipulate your vectors and access their various elements and combine vec3s with combining different dimensions of vectors, basically like vec2s and vec3s and vec4s. In this case, we are constructing a vector from a single float. So what that tells GLSL is that we want to create a vec4 where every element is 1. And then we're setting our output color, frag color, to this variable color. And so if we look at our viewer, we see that every pixel is white because R, G, B, and A are all 1. In GLSL, your color values are all in the range 0 to 1, which is how Touch works elsewhere, so that's pretty convenient. Okay, and if you're not familiar with the way that a shader actually works, like at the hardware level, like the way that this code executes, basically for every single pixel in your output image. So this is 256 by 256. So for every single one of those pixels, this function is going to be executed. So it's a very different way of thinking about code because this function is happening literally thousands of times in parallel. So it's just kind of worth understanding like how that actually happens inside of your graphics card. But it's not super important right now. What I usually do as sort of a sanity check when I'm first getting started is I want to color the frame buffer with our UV coordinate space. And what I mean by that is basically declaring a vector called UV. So it's a 2-element vector, and we're going to set that equal to vuv.st. So vuv.st is a built-in variable. It's a varying, which is again like it's another type of variable inside of TouchDesigner, or sorry, inside of GLSL. But it's not really important to know what that is right now. Basically, just know that Touch declares this variable for you. It is your UV coordinate of your current pixel. And if you're not familiar with UV coordinates, it's kind of a different way of setting up a coordinate space for your texture. So along kind of our horizontal or x-axis, we're going to call that our u-axis. And that's going to go from 0 to 1 on the right side. And likewise, our vertical or v-axis is going to go from 0 to 1, bottom to top. So what we can do to make that a little bit more clear over here is we can actually color our output image based on the UV coordinate of each pixel. So to do that, what we're going to do is construct our vec4 color from our vec2, which is UV, and then I also have to add another value here, another float. So we're constructing a vec4 from a vec2 and 2 floats. So together that will make a vec4. And this is an example of one of those different types of constructors that GLSL has for vectors. There's a lot of different ways to do this. So just getting familiar with the way that syntax works is definitely important. But anyways, now if we refresh our shader over here, we'll see that we are now coloring our UV space. And so the way to think about this is in the bottom left-hand corner, our UV coordinates are 0, 0. And if we look up here, back at our code, we can see that in the case that UV is 0, 0, our final color is going to be 0, 0, 1, 0, or sorry, 0, 0, 1, 1. In other words, there is 0 in the red channel, 0 in the green channel, 1 in the blue channel, and 1 in the alpha channel. So that's why in this bottom corner we have bright blue, 100% blue. As we move horizontally across the UV coordinate space, we see that we increase the amount of red in the color. And that's because U, the first coordinate of UV, is increasing. In other words, we are increasing the amount of red. Because remember, U here is basically being represented as our red channel. It then follows that up here in the upper right corner, we have white because U and V are both 1 up here, and so therefore we're back to kind of where we started, which is 1, 1, 1, 1, which is white. If that doesn't make sense, you should definitely sit with this code. It's simple. It looks very simple, but these sort of UV coordinate space manipulations and interpretations are going to be really important moving forward as we start to do more complex transformations, and especially when we start creating 3D geometry inside of this single shader. Like you have to understand how this space is laid out. So yeah, I would just really sit with that until it makes complete sense. So that's always a good sort of sanity check to do when you start writing shaders. So now getting back to the actual topic at hand of sign distance functions and ray marching. Distance functions, which are kind of the foundation for everything that you see inside of ShaderToy, are basically functions that return a distance. So you have a location in space, you pass it to this function, and it returns to you some sort of distance. And in later tutorials, I'm going to hopefully explain how that translates to 3D geometry, how we can actually create things like spheres and boxes and planes out of these basically math equations, not using any geometry. So it gets pretty theoretical, but for now, that's all you need to understand is that a distance function is a function that returns a distance, okay? And so I think the easiest way to understand that is by starting with a very simple use case. That is what we're going to do. So I'm going to declare a vec2 called center, and I'm going to set it equal to 0.5, 0.5. And so what this represents, what this coordinate, this vector is going to represent is the center of our canvas here, okay? So remember, UV coordinates go from 0 to 1 in both directions, so therefore 0.5, 0.5 is the center pixel. And now what we're going to do is we are going to color our canvas based on the distance from each pixel to our center point. And hopefully that will become more clear in a second here. So what I'm going to do is declare a variable, and just to be explicit, I'm going to call this dist to center. So this is the distance to our center point. And we're going to use a built-in function called distance. It takes two parameters, so in this case we're going to pass it UV and center, and it will return the distance between those two parameters, these two vec2s. So now this variable, for every single pixel, every time the shader runs, it will store the distance from that pixel to the center coordinate, or sorry, the center of our canvas. And we can visualize that in a similar way to how we visualized our UV coordinates with colors. We can visualize this distance as a shade of gray. So to do that, I'm going to actually use one of our vec4, overloaded vec4 constructors, where we basically pass it a vec3 and a single float. So this has 3 elements, and then the additional 4th element. From that we can create a vec4. And inside of this vec3, I'm going to pass it dist to center. So we're constructing a vec3 from this value. So every single component of this vec3 is going to be the same. It's going to be dist to center. Whatever that distance is, it will be stored inside of this vec3. And we're going to set this to our color, our final output color. And what you'll see is kind of a grayscale gradient, where each color represents the distance from that point to the center pixel. So that's why in the center here we have we have shades of gray that are much closer to black, because the distance is close to 0 at these points. And at the very center it is 0, which means that if we look back at our code, this vec3 will be entirely zeros, so we'll be basically passing 0, 0, 0, 1 to our output. In other words, black. The color will be black at the center. And then as the distance from the center increases, you'll notice that the colors become lighter, the shades of gray become lighter, because the distance is increasing as we approach the edge of our canvas. And since we're using the distance as a color, this value is increasing. And that means that we'll basically be approaching white. Now we're never going to hit full white, where this is basically what we started with, 1, 1, 1, 1, because the maximum distance that this is ever going to reach is from this corner to the center, and with some trig you can calculate that for yourself, but that distance from 0.5, a triangle with sides 0.5, 0.5, is actually something like 0.7, so it never reaches 1. But anyways, the important thing to notice here is that, or to see here, is that this is a distance field. This is called a distance field. We took our distance function, which was very simple. We just calculated the distance to the center from each pixel, and we used that to color our canvas, okay? Now where this starts to get interesting, there's 2 ways this starts to get interesting. The first is we can start clamping this distance field. In other words, we can choose to ignore all distances that are greater than a certain value. What I mean by that is, this will make more sense if I just write the code. I can create a variable called inside circle, and I can use another built-in function called step, and pass it two arguments. In this case, this is just a hard-coded value that we're going to start with 0.2 and dist2 center. This step function, what it does is it compares these two values, and if the second value, dist2 center, is greater than the first, it will return 1, and if it's less than the first, so if dist2 center is less than 0.2, it will return 0. So it basically partitions this space into either 0 or 1. And that will be extremely obvious once instead of using the distance field as our color, I use this new variable inside circle as our final output color. Okay, so now what we're doing is we're choosing to clamp our distance values at 0.2. So for any pixel where the distance from that pixel to the center is greater than 0.2, we're just going to return 1. In other words, white. That's why you see white all around here where the distance is greater than 0.2. And then for all pixels where the distance to the center is less than 0.2, we're going to return black. Okay, so we've basically just drawn a circle with a distance function. Okay, so this is very important to understand, this idea, because a lot of what we're going to end up doing, creating more complicated shapes in 3 dimensions, is this same idea, basically creating a distance field and clamping it at a certain value. You might even be able to imagine already how this would translate to 3D, where you can calculate distances in a 3-dimensional coordinate space, and at a certain point choose to clamp that value, and you would end up with a sphere. But we'll get to that. For now, it's just important to internalize this, this simple shader code. The other way that this starts to become interesting is if we take a step back, and I'm going to, I'm actually going to just delete that code and go back to our distance field before we clamped anything. You can combine these functions in interesting ways. That's how in later tutorials we will start to create more complex pieces of geometry in our scene, is basically by combining these distance functions. So again, I think the easiest way to explain that is to just see an example. So the first thing I'm going to do here is I'm going to actually shift this over. I'm going to shift our center point over a little bit in the U direction, in the horizontal direction. So now, if this isn't clear, basically, instead of comparing each pixel to the center of our canvas, I'm comparing it to this offset value, which is 0.2 in the U direction, 0.5 in the V direction. So this is our new center point. You can play around with these numbers and see how this distance field kind of changes as you move it around the screen, but it should be pretty obvious what's happening here. And what I want to do, what I want to demonstrate, is how we can combine 2 different distance fields. So what I'm going to do is I'm going to need to change some of these variable names really quick. We're going to call this center1, and we'll also call this dist2 center1. We're going to need to use center1 here, and then for now, just to avoid errors, we're going to rename that as well. So nothing should change. Now where this starts to get interesting is if I create another center point. And instead of 0.2, 0.5, I'm going to move in the other direction. I'm going to say 0.8, 0.5. And I'm going to do the same sort of calculation, except we have to give this a different name. We're going to call this dist center 2, and we're going to use center 2 inside of our distance function. So we've done the same calculation twice, nothing's changed. If we now create a final variable called combined distance fields, okay? I'm trying to be explicit here and just give these names that hopefully make sense. What we're going to do here is we're going to use another GLSL function called min, and it should be pretty obvious what that does, but it returns the smallest of the values that are passed to it. So we're going to give this dist to center 1 and dist to center 2. Okay, so what we're doing here again is we are basically seeing which of these two distances are smaller or shorter, or whatever you want to, however you want to think about it. Which distance is shorter? Am I closer to center 1, which is at 0.2, 0.5, or am I closer to center 2, which is at 0.8, 0.5, which you can't see right now, but if we take combined distance fields and we use that as our color, undefined variable dist, okay, dist to center 1, you get this kind of interesting pattern. So what we've done here is, again, is we've created two separate distance functions. One is the distance from our current pixel to 0.2, 0.5, and the other is the distance from our pixel to 0.8, 0.5. And we're combining those distance functions by taking a minimum, okay? So now for every pixel on our canvas, in our frame buffer, we are going to we're going to calculate which of those two distances is smaller and shade the pixel based on that value, okay? So that's why, you know, on the left half over here, you can see there's this very obvious vertical line where the distances are actually the same between those two values. And so that's why you get this striation right here, or this harsh division. On either side, the distance will be either closer to center 1 or center 2. So for example, if I have a pixel here, it's obvious that it is closer to center 1 than center 2, that's all the way over here. And so we're going to calculate that distance and set our pixel color to that value. There's a lot of different operations that you could do on these distance functions, and it's worth playing around with. I think the Book of Shaders has I think in the Shapes chapter, he talks a little bit about this, and it's worth reading it just to get a second kind of like overview of the technique. But anyways, he also talks about, you know, ways other than the min function that you could combine these two distance fields. And so it's worth sitting with this code and kind of going through these examples and shifting around, playing around with these coordinates, these center points here to really, really get a firm understanding for how this is being visualized and how these colors relate to distances, because everything that we do in the upcoming tutorials is going to be based on this premise, this basic idea of a distance function, and it won't make any sense if this part is confusing. So hopefully, I know it's nothing exciting yet, and we'll get there, but hopefully this sort of makes sense. And in the next tutorial, I think what I'm going to do is show you how you know, maybe we can start to animate some of these parameters, and there's going to be a point where we have to kind of make a big leap. It's going to be a longer tutorial to actually translating this technique to 3 dimensions, and there's also a lot of theory behind that. It's something that's very hard to explain because obviously we're not working with SOPs, we're not working with a camera or lights or geometry like you normally would in Touch. And so the idea of creating a 3D space inside of a single shader is not intuitive by any means for most people, I'm sure. So hopefully I can help. I'm going to try to help clear that up, and we'll go through some examples. And then I also want to talk about, as I learn more about these things, what are some of the use cases of them? Because I think like a lot of people, you know, they look at ShaderToy and they understand that it's complicated and it's interesting, and there's something there, there's some creative potential there, but I don't think that a lot of people understand why we would want to use these things, and why they are so powerful. So that's hopefully something that I'll cover in a later tutorial as well. But for now, if you're interested in the technique and just learning, hopefully this starts to become interesting in a little bit. Thanks for watching.